All right, can you hear me? Yep, okay, good. Any questions before we start? We're about to move on to a new and exciting topic in wildlife population dynamics and modeling them.
Barry, could you make an announcement about the 2 lab questions that
Yeah.
I think it's like
It's 2 part 3 or something like that. Let me pull that up so I know exactly which one it is. So in the lab, labs, this is lab 3.
Julian's birthday today. Yeah.
Whose birthday is it?
Oh, it's my friend Jillian's birthday.
Oh, it's no one from class?
No, sorry.
Oh. All right, so in lab 3, we have question 2, part 4, part 1V, says simulate 100 new data sets from the fitted model, plot all of the simulated data on one graph, and plot the real data on top of the simulated data with counts on the y-axis and precip on the x-axis. And if you downloaded an early version of this lab, it doesn't say with counts on the y-axis and precip on the x-axis. Regardless, this question is not going to be graded in the lab. And the reason why is because it requires plotting 3 dimensions. So it would require plotting plots on a plane and having 3 axes, an x, a y, and a z. And in lab 2, we talked a little bit, we didn't talk about it, but at the end of lab 2, there was a just for fun section on R and plotting 3D, but we haven't formally talked about that. So part 4, take a look at it, think about it, but it's not going to be graded. It won't be graded for the lab assignment. Same thing with part 7, if, it's question 3, part 7. You're going to go through your model selection for spotted owls, and you're going to find a top model. If your top model has more than 1 covariate, then you don't need to do part 7. Now this is going to depend on what your model set looks like. However, if your top model does have 1 covariate, then attempt part 7 in question 3. And this is just like the last question in lab 2. Very similar, except we're storing our y data and not our beta data. Our beta values, our y values and not our beta values. Yeah. Any questions about that? Are there any other announcements, Julie?
I don't think so.
Okay, I have a couple things here. So we voted in lab on both Monday and Wednesday, and an overwhelming majority wanted to record labs ahead of time. So we're going to start that. Well, I'm going to record lab 4 today during lab. So we'll have a live lab today. And then on the Monday's lab, can view that lab beforehand and come to lab prepared to work on the lab. And then from then on out, I'm going to record, starting a week from Wednesday, I'm going to record it completely ahead of time, try and post it by Sunday so that, let's see, Wednesday's lab, you'll have 3 days, Monday, Tuesday, you have at least 2 days to watch the lab and then come to lab after viewing it, and then spend the time in lab working on the lab instead of watching the lab. So starting Monday, you'll have a pre-recorded video to watch before coming to lab. Labs will then be shorter because I won't spend an hour talking about what we want to learn. That'll be already covered. However, you'll have some homework to do beforehand. Any questions about that or concerns? Okay, the next announcement is I'm going to post some practice problems, probably over the weekend. I did this for simple linear regression already, but I'm going to start posting practice problems so you have an opportunity to get a little more work with this if you choose, if you feel like you'd like to see some more examples. These practice problems won't be graded, but you can ask about them, ask anything about them in either class or office hours. Okay, and then my last announcement is our first exam. It's a take-home exam. I'm going to write the exam and then figure out how many days you'll need to do this. But it will be basically analyzing data. I'll give you some data sets. You'll have to analyze the data, interpret the parameters, interpret your results, and then discuss the population and what's going on. If there's management actions involved, the alternatives for management will be described in the question, and what management actions to implement will be based on your analysis. So the idea is there's a question of interest. We have some data that we've collected on the population. We need to analyze that data to help inform our management actions. So it'll be a combination of thinking critically about what we need to do, taking some data in hand, analyzing that data, interpreting the results, and then applying those results to making decisions. The material for the exam will cover model assessment, and I'll have a slide on this coming up, but it's model assessment, simple and multiple linear regression, and then generalized linear regression, which we're going to get into today. Any questions about that? The exams you'll be working on independently. Yeah. Okay. All right, so let's get into, if there are no questions, let's get into the lecture material. I can hear someone chewing. I don't know who it is, but if you're chewing, you might want to mute your mic. Okay, there we go. All right, so here's lecture 7. We're on, I think, week 4 of the semester. And we're going to be talking about generalized linear models. So we talked about simple linear models and multiple linear models already. Now we're talking about generalized linear models. And this lecture and next lecture are going to focus on binomial regression models. So in a statistics class, we have a lot of different types of data, and what we try and do, if you've taken an introductory statistics class, you probably haven't talked about generalized linear regression. You've probably talked about linear regression models and fitting a line to data or a plane to data if you have more than one covariant. But what we do in those classes, in those simple linear regression models for non-stats majors, is we teach what to do if the data don't meet the assumptions of normal regression. And there's pretty much one tool that we use to try and smash our data into the assumptions of normal regression models. Any idea what that is? And this isn't something we've talked about in this class, but
What was that question?
the question is, we have data, we know we've talked about simple and multiple linear regression models. And if you take an introductory stats course on any introductory stats course, you might talk about linear regression models. And if you don't meet the assumptions of linear regression models, there's pretty much one tool that's taught so that you can meet those assumptions. What is that tool?
Would that be log transforming it?
Yeah, exactly. Transforming the data. If you don't meet the assumptions of a linear regression model, you transform the heck out of it. You take the log, you take the square root, you basically do whatever transformation you can do until you can use that tool of linear regression models. So that's where this quote comes from. When all you have is a hammer, everything looks like a nail. So if all you have in your toolbox is linear regression models, the only thing you can do is make everything look like a linear regression model, and that's what we do by transforming it. However, there are a lot of other tools out there. And starting now, we're going to talk about some of those other tools for the data types that we experience a lot in wildlife ecology. So where have we been so far? We have talked about model evaluation, and this consists of two components. Checking model assumptions, that is, if they meet the assumptions of our linear regression models, and then choosing if they do meet the assumptions and we have more than one model, which model do we choose? So we talked about model selection using AIC, Akaiki's information criterion. The three assumptions that we've talked about are for linear regression models, for simple and multiple linear regression models. And those are the data independent? Are the data appropriately distributed? Before this slide right here, I had, are the data normally distributed, or are the residuals normally distributed? We're going to talk about other distributions besides the normal distribution. So that's why I changed this to appropriately distributed for this slide. And then is the variance the same for all values of the covariates? Or more concisely put, is it homoscedastic? And then, okay, so all of this goes along with model evaluation. We're going to always talk about model evaluation when we're modeling data because it's always an important step. The types of models we've talked about so far are linear regression models, and those include simple linear regression and multiple linear regression. And now we're going to go beyond that. A lot of the same principles for these models apply for what we're going to cover next. So that's why it's so important to have a solid foundation in linear regression modeling. Okay, so where we are going. We're still going to talk about model evaluation throughout this course. And the assumptions of our models are going to change a little bit, but this is always an important step, model evaluation and model checking and model selection. But now we're going to move into a new class of models called generalized linear models. Within generalized linear models, there's a lot of different types of models. There's binomial regression, Poisson regression, beta regression, and a bunch of other ones, but these are the main ones that we're going to discuss in this class. So binomial regression is probably the most used type of model in wildlife ecology. It includes things like analyzing survival of a population, estimating occupancy or distribution of the species, where a species is and where a species isn't. Detection probability, we've talked about this a little bit. Wildlife don't like to be seen. So how do we model this probability of actually seeing an animal given it's there and that it doesn't want to be seen? Habitat selection, which habitats are animals using and which ones aren't they using? This is what we're going to talk about in the next two lectures, binomial regression. And then after that, we're going to talk about Poisson regression. Poisson models are used for count data, and we also have lots of count data in wildlife. We like to count populations, see how many there are. Beta regression's used for looking at values between 0 and 1. So if we have proportions. All right, so this is where we're going. And this is the slide I was talking about earlier when I said the test material are going to cover up through generalized linear regression models. We have a lot to cover in generalized linear regression models still. And I'll take a look at my slides, see how many lectures we have left, and then post our exam date. All right, let's talk about binomial regression. Binomial regression is a type of generalized linear regression. And let's start off with an example. And this is a very common type of analysis and study used for wildlife populations. We're going to focus on Arctic geese survival, estimating what the survival rate for the population of Arctic geese are. Recall that our population model, our most basic model is our VIDE model, where we have the population size at time t plus 1 equals the population size at time t plus the number of births into the population, plus the number of immigrants into the population, minus the deaths, minus immigrants. So the number of deaths is an important component of that population. And how we can estimate that is estimating survival rates. So how do we estimate survival? Let's open this up for discussion a bit. Just looking at, say we have a population out here. What is one thing we can do to estimate survival?
Well, there's a couple ways depending on the species. I know it's common with game species to have, if the animal's marked, hunters turn in the marks, so therefore you have some idea of who's getting hunted. And with mark recapture, you can kind of see who returns every year and theorize, depending on the species, if they're dead or not. Some species live so long it's not viable, but some species have such a short life range that can work.
Yeah, so you mentioned I updated my iPad and now my pencil doesn't work, so I got to do this on paper here. Take notes on paper. You mentioned hunters turn in bands, and you also mentioned mark recaptures. Yeah, and those are two important data types that we can use to estimate survival, and we'll talk about both of those in this class. But let's think about that a little more too. Let's extend on that. We have mark recaptures, we have bands. What do we do with that? So what are the sources of information we have when we do either one of those types of analyses? I mean, think about an Excel spreadsheet. What are we gonna, what's our basic information that we have?
I'll answer again. You kind of have how many animals you've marked in total. That's always going to be something you should have kept track of. And depending on how you're capturing them, I mean, I know some data bands can tell you when the animal's still for too long and probably dead. I know that Kelly Stewart does that with deers. And you probably—
Are you talking about radio telemetry now?
Oops, sorry, I moved. Never mind. Yeah, sorry, my brain's moving different places.
No, that's all right. It's a discussion.
Number of animals you have, probably a population estimate at the very least of the area for marker capture. Again, depends on the species and how much you're able to actually tell how many animals are there.
So how many animals you marked, how many animals are there?
A general population estimate.
Okay.
You'll also get the location of where the animals are either captured or seen by hunters.
Location of marked animals or all animals?
Of the marked animals that you see. That you
Okay,
count.
so we're bringing space into this now. Okay, I like that. Location of marked animals. All right, so you have an Excel spreadsheet. You plug in how many you went out and captured some animals. You kept track of how many you captured and how many you marked. And then you go back to the office and you open an Excel spreadsheet and you type in, on this day, I marked 100 animals. And then you also mentioned, okay, we went out again another day, maybe a week later. We looked for some animals and you're recording the location of where you saw those animals. Okay. What else? What else we need to know to put in that spreadsheet?
Did you also get the number that have been like recaptured multiple times?
No, we haven't talked about that yet. So you go out, day one, you go out and capture 100 animals. You come back to the office, you write down maybe the band numbers that you capture. So you've got 100 rows, I equals 1 to 100 in your Excel spreadsheet. Let me just open a spreadsheet here. And we can work through this, okay. All right, so we went out, we set up some traps, and we had some unique bands, maybe some leg bands, some neck bands like we saw in that previous picture, that yellow band of cackling geese. We put those on some geese, and we have unique identifiers. We have, let's say, I equals 1 to 100. Okay, there's our eyes. And let's say that the neck bands were just numbers 1 to 100. Keep it easy. Usually we use some other type of marks and indicators, but this makes it simple for this example. These are what their neck tags say. All right, a week later, we go back in the field, right? And we recite some animals. And so Leah, this is what you were saying. We keep track of the ones we saw. So what do we do now with our Excel spreadsheet? What's one thing we could do? So these are all the animals we saw. What can we do next? We come back to the office. We have our notebook with all of our sightings. What should we add to our spreadsheet here?
For each column, you can set it as each time that you went out and looked for them. And then for each one, you can just say whether you saw them or not.
Oh, okay. Good. All right. And also we could have, let's see, we'll call this week 1, week 2, and so on. Now, I'll add a couple things. We talked about location, so we could say location. We could include some maybe X and latitude, longitude information for location. There's other information that we've talked about, how many animals there are. We'll talk about that more too. But so Becky, you said whether or not we saw them. So we could write saw it, didn't see it. For each of our animal, whether or not we saw animal 1, animal 2, animal 3, and so on, we could fill this in. Right. So what is this? This is saw it or didn't see it. It's an option of 2, right? It's like a coin flip, a heads or tails. So let's just convert this to a 1 if we saw it, and a 0 if we didn't see it. And I'll just fill these in some randomly here. Oops, we don't have any 2s. Most of them we don't see because it's a hard to see species, we'll say. You see a few of them. I'm filling these in randomly. If I was using R, I would use a function analogous to R norm for this. Okay, so I'm generating some data. I did 30 of them. And you can imagine we could fill in the rest. Let's say we didn't see any of the rest. I'll just fill it in. Okay, so we only saw 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 100 of them. The second week we went out. Let's add one more column here too, just to solidify this point here. Let's just put the first time we went out and captured them, we saw all of these animals, right? So we'll say week 0. This is our capture week. Because we saw all of them, let's just put a 1 here for all of the ones we captured and saw. Okay. All right, so we've got some data now. These are essentially the type of data we'll be working with for binomial regression, specifically Bernoulli regression. Now, what are some issues? So let me just say to start off with, when we mark an animal and we go out and look for it, there are 3 possibilities that could occur. The first possibility is it survived and we saw it. What are the other 2 possibilities? Think about that for a second. All right, any volunteers?
It could be alive, but you didn't see it.
Exactly. It could have survived. We just didn't see it. And what about the third possibility?
Maybe it died.
Yeah, it could have died. And those are the 3 possibilities.
Quick comment, isn't there a 4th possibility that the band fell off without us knowing? I know that can happen in some times.
That's right. Yeah, that's exactly right. And one of the assumptions, we're getting a little ahead of ourselves moving on to the next module. I'm getting a little ahead of ourselves moving on to the next module when we're going to talk about mixture models. But one of the assumptions in capture recapture that we have to make is that no bands, we had no mark loss, no tag loss, because otherwise there's this 4th possibility that we have trouble modeling. Right, so there's a 4th possibility, and we're going to assume that away, assume that that doesn't happen by using bands that don't fall off. All right. So let's simplify this a little bit, because we're just getting started on binomial regression. We're going to build in the complexity of these 3 different options later. Let's assume that if it's alive, we're going to see it. The detection probability is going to equal 1. And we'll relax that assumption later on. So now we're back to just 2 possibilities. And this is just going to help introduce the methods, and then we'll add the complexity later. So if it's alive, we're going to see it, guaranteed. Maybe these are animals with radio tags on them, and we can ohm into where they are and see it. Okay, now if it's alive, we're going to see it. That means we're going to have a 1 here. So this means that all the zeros here mean that the animal actually died. What would be a naive way to estimate survival probability?
By thinking that just the ones that you see are the ones surviving?
Just the ones that have 1s in this column are the ones that survived. Yep.
Since you only have 1 week of data, isn't the probability just exactly what it is that week?
Can you elaborate on that a little bit?
So if you saw 7 or 8, then it's a 7 or 8% chance of survival. And then
Because we have 100 observations, right?
Mhm.
Yeah. Yeah, if we had 30, it would be a little different.
Yeah.
Yeah. So, yeah. So what Becky's saying is, let's add up all of the ones we saw here. We can just say, see if I remember my Excel commands. We saw 9 here. We can add up all of these ones. You can see why I put this column of ones here. And then say, survival probability equals this divided by this. 9%. So maybe this is a kind of doomed population here. 9% survival is pretty low. Maybe if, yeah, especially for 1 week. It's like gerbils. Okay, right, so that's how we could naively estimate survival probability. The idea is we're starting off with some number, some big number. Here, all of these. And then we're collecting information. Our data are going to consist of ones and zeros. And we're going to try and estimate some probability of survival. Now, this was, let's see, I'm going to make this a little more realistic for our goose example, our Arctic goose example. But it's the same idea. We mark a bunch of geese, we capture a bunch of geese, we mark them. We let them go, and then we go out and see which ones we see again. If we see them, it gets a 1. Our column gets a 1. And if we don't see them, it gets a 0. Those are our response data. Those are our Ys. So our data have changed now from what we were talking about before, where we measure home range size or number of elk or spotted owl home range size. I already mentioned that one. Avian species richness. We're going from like a count or a size or some number that can be big to just zeros and ones. And we need to use a different tool for these types of data. And that's where Bernoulli and binomial regression come in, and generalized linear regression comes in general. All right, so that's exactly what we do here. We capture a bunch of geese. These are cackling geese. They look like a Canada goose, except they're about the size of a mallard. So it's like a miniature Canada goose. They breed in the Arctic. There's some other pictures here of another Arctic nesting goose that are coming up called Brant. And Brants also breed in the Arctic. And we're interested in the survival rates of these populations. So how do we get that data? Well, we go up to Alaska. This is way up on the north slope of Alaska, Teshekpuk Bay. It's a big oil area. This area is actually protected because the geese come here in about June, July to molt. So a big portion of the population fly to these lakes in Alaska. They shed all of their feathers so they can't fly. And then they regrow new feathers. And this is a good place for that because except for this Arctic fox here, they're relatively safe. And they need to be safe when they can't fly. So they come up here, they do this molt migration, it's called, they migrate to Teshekpuk Bay, and that gives us an opportunity to capture a large number of geese. So they get in these big flocks like this, and none of them can fly. So we can herd them up into these capture nets, mark them, give them marks. So these are brant here. Herd them up in these capture nests. They can't fly, so we can capture them safely and let them go. We herd them into these areas. And then we hand them over to people who are going to put bands on them. They're going to put a metal band on their leg, a unique USGS band on their leg, so that if hunters shoot them, they can turn in those metal bands and we can record where they went. Someone mentioned marking the location of where they were found to look at spatial characteristics. We know exactly when they were captured and how long they survived. Here, this is a brant. Here's a leg band on this. This brant also has a VHF transmitter coming out. It's hard to see, but it has a VHF transmitter coming out so we can radio track it. We're not talking about those data explicitly right now. We can talk about those later. And then after releasing them, we go out and we look for brant at known brant locations, and we try and find the ones that we marked. We look for yellow bands. And we get that data exactly those data that we just discussed, those ones and those zeros. There is additional information here too. We will talk about these information later, but someone mentioned counts of unmarked individuals. We can also count up how many are here that didn't have bands, and we'll use those later in what we call Lincoln-Peterson estimators. But right now we're focusing on whether or not we see individuals that were marked. And here's what we set up already. So for now, we assume that if individual is alive, we will see them with probability 1. And we're going to relax this assumption later when we talk about mixture models. So we have a goose ID, and then we have whether or not they were alive or dead. Something we haven't talked about yet in generalized linear models is we can do the exact same thing we did in simple linear regression and multiple linear regression modeling. And that is we can also collect covariate information on the geese when we capture them. So if we go back here, we see these guys down here with this guy's banding, this guy's getting some length measurements here. So while we're capturing them, we can also collect additional information on them. And we can store that information as covariates. And we can start to ask questions like, does size of the bird affect its survival? Do larger birds survive better than smaller birds? We can collect more than just length. We can collect all types of information. And we want to collect this information to ask our hypotheses about why a bird survives from one period to the next. All right, so we're just going to extend our linear regression models so that we can use these types of data. Before we had yi's could be any value between negative infinity and infinity, and this model would work. So this should be familiar by now, where we have yi, we assume comes from a normal distribution with a mean described by mu I, or an expected value described by mu I. And this mu I depends on the covariates that we're interested in. And then there's going to be some variability described by sigma squared. And we plug in to R, our yi's and our xi's, and then R gives us an output table on what all of our betas are here and what our sigma squared is here. And we fit our regression model, and then we can make inference about this population. But now if we put 1s and 0s in here for yi, this isn't going to give us very good results. We talked about putting 1s and 0s in for the x's when we were talking about t-tests. I think this was lab 2. That's okay. We can always put 1s and 0s in for our x's, but we can't use this framework to put 1s and 0s for the y's. All right, so this is what I said already with the Arctic goose data. Yi is not normally distributed. They are 0s and 1s. So we need a more flexible framework to deal with these types of data, or a more general framework, and that's why we get the name generalized linear regression. We're still going to be interpreting things very similarly, except we need something that allows us to deal with these 0s and 1s. All right, so a random variable is something that you observe that changes every time you observe it. And we've talked about normal random variables so far. We've mentioned a little bit of Poisson random variables. So here's a question: what type of random variable results in 0s and 1s?
Binomial.
Yeah, it is, that answer is correct. There's a specific type of binomial that we're going to deal with for 0s and 1s. Do you want to expand on the binomial?
Is it the Boolean?
Yeah, Boolean or Bernoulli is the name of the distribution. It deals with Boolean data. So Boolean means either true or false, less than, greater than, equal to, but we're going to talk about Bernoulli random variables. Bernoulli random variable is a specific type of binomial random variable where we're only doing one trial. So let me state the differences here, because this is an important distinction. A Bernoulli random variable is like a coin flip, one coin flip. It's either going to be heads or tails. You could say a 1 is heads and a 0 is tails. And that is a specific case of a binomial random variable. A binomial random variable would be, you can do as many flips of the coin as you want, and you're just going to add up how many heads you got. So a binomial random variable is you do some coin flips, you count how many coin flips you do, and you count how many times you got a 1. So that's a binomial random variable. A Bernoulli random variable is you just do one coin flip, and you say whether it's a 0 or 1. So we're going to treat all of these birds, or all of these animals in our population, like individual binomial random variables, where if we saw it, it's going to be a 1, and if we didn't see it, it's going to be a 0, and we're going to try and estimate the probability of observing a 1. If we go back to make one more distinction between Bernoulli and binomial, if we go back to our Excel sheet, each one of these is one Bernoulli trial. We have 100 Bernoulli trials. If we add them all up together, this is a binomial random variable, where we had 77 successes out of 100 potential successes. All right, so our response data here, YIs, are 0s and 1s. We are going to say, here's where our first change comes. YI comes from a Bernoulli distribution. So we used to say normal here. Now we're saying Bernoulli, with some probability of success, mu I. And we're going to relate mu I to our covariates. This would be, in the case of our banding data, this would be, for example, X would be the length of each individual bird. X, this X could be if it was a male or female. And we could have as many of these in here as we want, as we have data for on individual animals. So there's 3 important differences in this model compared to our normal linear regression models. The first one is we're using a Bernoulli distribution here to describe, to help with our 0-1 data. The second important difference is this mu value is going to be some function of these covariates. So F stands for function. And we'll talk a lot about why we need some function here. The third important difference is there's no sigma squared here. We don't have a parameter for sigma squared. The variance isn't something we estimate by itself. The variance is a function of the Bernoulli random variable. Mu I represents the probability of success, the probability of observing the animal. In the case of a coin flip, we know that mu I is 0.5. But in the case of Arctic goose survival, it's going to be something higher than that because they're going to survive with higher probability than 50% from 1 week to the next. All right, what values does mu I have to be between? It's a probability.
0 and 1.
Yeah, that's right. That's a difference too between this this model and linear regression models. We've already talked about that difference though. So if we know mu I has to be between 0 and 1, we're going to need to transform these values here, this whole equation here, to be between 0 and 1. Remember what this equation was in simple linear regression. This was the equation of a line. And there was nothing that restricted that line between 0 and 1. It could be negative, it could be positive, it could be anywhere between negative infinity and infinity. And in fact, all lines are between negative infinity and infinity, all straight lines. So we're going to have to do something to that line to make it bend between 0 and 1. And that's what this function does. This function here, we haven't talked about what function it is, but it's going to convert this line, it's going to bend this straight line that we saw before to be restricted between the values of 0 and 1. Any questions on that? What is the function that f is? Well, we're going to use the inverse logit function. And we'll talk about how to calculate this. But it's basically we do some stuff to this. We put this in an equation. I can't get this done. Just get that page. There we go. We do some stuff to this line to make it bend between 0 and 1. And that's called the inverse logit function. Okay, so with our Arctic goose survival data, we have zeros and ones. These data suggest a Bernoulli distribution. Remember, the zeros and ones are just the response data. We can have all kinds of other information in our covariates, but we're talking explicitly about the response data, the zeros and ones. And this is our model that we're going to use. This is Bernoulli regression. And we'll talk about interpreting and fitting these models next time. Okay, it's 9:50. Any questions? I have office hours now. And I'll just stick on here through office hours. Thank you.
Have a good day.
You too.